Welcome to this walkthrough of problem number 688, Knight Probability in Chessboard. In this problem, we'll explore a fascinating dynamic programming challenge involving a knight's movements on a chessboard. Stay tuned as we dive into the approaches and strategies to solve this problem efficiently. In this problem, we are tasked with calculating the probability that a knight remains on an NX in chessboard after making exactly k moves. To understand this, we need to recall the unique movement of a knight in chess. A knight moves in an L shape, which means it can move two squares in one direction and one square in a perpendicular direction. This gives the knight up to 8 possible moves, such as moving 2 steps forward and 1 step to the left, or 2 steps backward and 1 step to the right. However, not all of these moves will always be valid since some may take the knight off the chessboard. The knight starts at a specific position, given by its row and column, and we need to determine the probability that, after k moves, it is still within the bounds of the board. Now, let's look at the input and output of the problem. The input includes the size of the chessboard, n, which can range from 1 to 25. We are also given k, the number of moves the knight will make, which can range from 0 to 100. Additionally, we are provided with the initial position of the knight, specified by its row and column indices. These indices are zero-based, meaning they start from 0 up to n1. The output of the problem is a single floating point number representing the probability that the knight remains on the chessboard after k moves. For example, if the knight is guaranteed to stay on the board, the probability would be 1.0, while if it is certain to move off the board, the probability would be 0.0. Let's go through an example to understand this better. Suppose we have a 3x3 chessboard, and the knight starts at position 0, 0. If the knight makes 2 moves, there are a total of 8 possible moves in the first step and 8 more in the second step, giving 64 potential paths. However, many of these paths lead the knight off the board. In fact, only 1 out of the 64 possible paths keeps the knight on the board. This means the probability of the knight staying on the board is 1 divided by 16, which is 0.0625. Another example is when the knight starts on a 1x1 chessboard and does not move at all, as k is 0. Since the knight doesn't move, it remains on the board with certainty, resulting in a probability of 1.0. Let's consider another example with an 8x8 chessboard, where the knight starts at position 4, 4, and makes 1 move. From this central position, the knight has up to 8 potential moves. However, if some of these moves land outside the bounds of the chessboard, they are invalid. In this case, exactly 6 out of the 8 moves keep the knight on the board. Therefore, the probability of staying on the board is the ratio of valid moves to total possible moves, which is 6 divided by 8, or 0.875. This illustrates how the knight's position and the size of the board influence the probability calculation. To summarize, the problem imposes some important constraints. The chessboard size, n, ranges from 1 to 25, ensuring that the board is always manageable. The number of moves, k, can be as high as 100, which means we need an efficient way to calculate the result. The starting position is always valid, as it lies within the bounds of the board. Additionally, the probability result must be accurate to within 10 to the power of -5 of the true value. Edge cases include situations like when k is 0, where the knight doesn't move and the probability is always 1.0, or when n is 1 and any k greater than 0 results in a probability of 0.0 because the knight cannot move without leaving the board. Furthermore, starting near the edges or corners significantly reduces the knight's valid moves, lowering the probability. Lastly, as k becomes very large compared to n, the probability approaches 0, since the knight is more likely to move off the board over time. To solve the knight probability in chessboard problem, we start by considering 2 main approaches, the brute force method and the dynamic programming approach. The brute force method is the most intuitive. Here, we simulate all possible movements of the knight across the given number of moves. Starting from the initial position, we recursively explore every one of the knight's 8 possible moves at each step. For every move, we check whether the knight remains within the boundaries of the chessboard. Once all moves are simulated, the probability is simply the ratio of valid moves, where the knight stays on the board, to the total moves simulated. However, this approach rapidly becomes inefficient. Since each move leads to 8 new possibilities, the time complexity grows exponentially, reaching 8 to the power of k, for k moves. Additionally, the recursion depth requires OK space. This makes brute force impractical for larger chessboards or higher numbers of moves, as it redundantly calculates probabilities for the same positions multiple times. This inefficiency motivates the need for a more optimized approach. Dynamic programming, on the other hand, leverages the fact that the knight's position at any step depends only on the positions it could have reached in the previous step. This overlap between subproblems makes DP a natural fit for solving this task. By using a 3D DP table, where each entry represents the probability of the knight being at a specific cell after a given number of moves, we can efficiently compute results step by step without redundant recalculations. The base case starts with the knight's initial position having a probability of 1, while all other positions are initialized to 0. For the transition, the probability of reaching any cell is derived from the probabilities of all cells that could have moved to it in the previous step, divided equally among the 8 possible moves. This eliminates redundancy and ensures that each unique state is computed only once. With this, we achieve a time complexity of O(k*(n squared, which is a significant improvement over the brute force approach. Dynamic programming not only improves time complexity but also allows for potential space optimization. Initially, the 3D DP table has a space complexity of O(k*(n squared, as we store probabilities for every step, row, and column. However, since each step only depends on the probabilities from the previous step, we can reduce this to O(n squared by maintaining just two 2D tables, one for the current step and one for the previous step. Another alternative to iterative DP is using recursion with memoization. This method calculates the probability for any given step and position recursively while storing already computed results in a memoization table. By doing so, we avoid redundant recalculations and achieve the same time complexity as iterative DP, O(k*(n squared). However, memoization introduces an additional space requirement due to recursion depth, which is OK. While this recursive approach is easier to implement and may feel more intuitive, it can run into stack overflow issues for larger values of k due to deep recursion. Considering these options, we select the dynamic programming approach as our primary strategy. It balances clarity, efficiency, and scalability. Brute force is infeasible for larger inputs, and recursion with memoization, while elegant, can face limitations with deep recursion. DP, especially with space optimization, offers a structured and scalable solution, making it suitable for both small and large chessboards as well as varying numbers of moves. Each approach has its own trade-offs. Brute force is straightforward and easy to implement, making it a good starting point for understanding the problem. However, its exponential time complexity makes it impractical for larger cases. Recursive memoization improves efficiency by avoiding redundant calculations, but it can encounter recursion depth limits, especially when the number of moves is large. Iterative dynamic programming addresses these issues by avoiding recursion entirely and providing a more structured methodology. It does require careful design of the DP table to ensure correctness and efficiency, but it avoids the pitfalls of stack overflow and redundant computation. By choosing the iterative DP approach, we strike a balance between time and space efficiency. With a time complexity of O(k*(n squared and space complexity reduced to O(n squared through optimization, this method is well suited for solving the problem across a broad range of input sizes, from smaller boards to larger ones requiring many moves. This balanced solution ensures the knight's probabilities are computed accurately and efficiently, making it the most robust choice for this problem. To solve the knight probability in chessboard problem, we start by understanding the task. We are working with an NX chessboard, where a knight begins at an initial position, x, y. The knight can make up to k moves, and our goal is to compute some property, such as the probability of the knight staying on the board after these moves. The knight moves in an L shape, so there are exactly 8 possible moves it can make, 2 steps in one direction and 1 step perpendicular to that, or vice versa. These moves include combinations like x plus 2, y plus 1, or x1, y2. These movements will form the foundation of our recursive approach, as we simulate the knight's possible paths step by step. The core of our approach is recursive exploration. Starting at the knight's initial position, x, y, we initialize a move counter to 0. At each recursive step, we need to first check if the current position is within the chessboard's bounds. If the position is out of bounds, that particular branch of recursion is terminated. If the knight has already made k moves, we return the result for this branch, which could contribute to the total number of valid sequences. Otherwise, we recursively explore all 8 possible moves from the current position. To handle edge cases, we define 2 base conditions. If the knight steps out of bounds, we return 0 for that branch, as it represents an invalid sequence, and if no moves remain, we return 1 only if the current position is still within bounds, otherwise 0. Finally, we combine the results of all 8 recursive branches to calculate the total. To make this approach more efficient, we can optimize it using memoization by storing the results of subproblems in a DP table, so we avoid redundant computations. The recursive tree generated by the brute force approach can grow exponentially, with up to 8 k branches, as the knight has 8 possible moves at each step. While this provides a complete exploration of possible paths, it is computationally expensive. Memoization significantly reduces this complexity. By storing the results of previously computed subproblems, we ensure that each unique state defined by a position, x, y, and the number of moves left k, is calculated only once. This optimization brings the time complexity down to n squared asterisk k, where n2 accounts for all positions on the board and k accounts for the number of moves. This is possible because the result at any given position depends solely on the current state, making it an ideal candidate for dynamic programming. It's important to consider edge cases too, such as when the knight starts near the edge of the board, when k equals 0, or when the board has a minimal size, like n equals 1. To implement this solution effectively, we rely on specific data structures. The most critical is the memoization table dp, x, y, k, which stores the results of subproblems. This table has dimensions nx and x, k plus 1, where n is the board size and k plus 1 accounts for the move counter from 0 to k. By storing results in this table, we avoid recomputing the same state multiple times, drastically improving efficiency. For alternative iterative solutions, such as a breadth-first search (BFS) approach, we could use a queue to simulate the moves step by step. While BFS can be a viable option, the memoized recursive approach remains a more direct and intuitive way to solve this problem. The key operations in this algorithm include recursive calls, memoization lookups, boundary checks, and result combination. Recursive calls are made to explore all 8 possible moves from the knight's current position. Without memoization, this would lead to a time complexity of 8 to the power of k, but memoization reduces it to n squared asterisk k, by ensuring each unique state is computed only once. Boundary checks are essential to ensure that the knight stays within the board's limits during its moves. Finally, the results from all valid recursive branches are aggregated to compute the total outcome, whether it's the number of valid sequences or the probability of staying on the board. These operations work together to ensure the algorithm is both correct and efficient. To further enhance the performance of this solution, we can apply several optimizations. Pruning is one such technique, where branches that go out of bounds are terminated immediately, saving unnecessary computations. Memoization remains a key optimization, preventing redundant calculations by storing results of already solved subproblems. Additionally, the recursive solution can be converted into an iterative one using a BFS or dynamic programming table filling approach to better manage stack usage and allow for more controlled iterations. Each of these optimizations ensures the algorithm runs efficiently, even for larger boards and higher values of k. Here, we start by defining a class called solution and implementing the knight probability function. This function calculates the probability of a knight remaining on an NX in chessboard after making k moves, starting from the given row and column. To do this, we first define all the possible moves a knight can make on a chessboard. These moves are represented as coordinate changes in the directions list. For example, 2, 1 means the knight can move 2 steps vertically and 1 step horizontally. Next, we introduce a memoization dictionary to store previously computed results, which helps avoid redundant calculations and improves efficiency. After that, we define a helper function called DFS, which performs a depth-first search to recursively calculate the probabilities. Inside DFS, the first thing we check is whether the knight has moved out of bounds. If so, we return 0 since the knight is no longer on the board. Then, we check if the knight has no moves left. In this case, the knight is guaranteed to remain on the board, so we return 1. Finally, before proceeding with further calculations, we check the memo dictionary to see if the result for the current state has already been computed. If it has, we simply return the stored value to save computation time. Now, we move into the recursive part of the DFS function. For each possible knight move defined in the directions list, we recursively call DFS to calculate the probability of the knight staying on the board after making that move. We decrement the moves _left parameter by 1 to reflect that the knight has used one of its moves. The probabilities from all possible moves are summed up in the variable prob. Once all moves have been considered, we calculate the average probability by dividing prob by 8, since the knight has 8 possible moves. This average probability is then stored in the memo dictionary with the current state as the key, so we can reuse it if the same state is encountered again. Finally, the function returns the memoized probability for the current state. To start the calculation, the knight probability function calls DFS with the initial position of the knight and the total number of moves k. This initiates the recursive process and ultimately returns the probability of the knight staying on the board after k moves. To solve the knight probability in chessboard problem, we start by defining the possible moves a knight can make on the board. These are represented as an array of coordinate changes, where each pair corresponds to a specific move. For instance, 2, 1 means moving 2 steps in the vertical direction and 1 step horizontally, and so on for the other directions. Next, we introduce a memoization map, which is a hash map that helps store and reuse previously computed results. This is crucial for optimizing the recursive solution and avoiding redundant calculations. The main function then calls a helper method, DFS, which performs a depth-first search to recursively calculate the probability of the knight remaining on the board. The parameters passed to DFS include the board size, the number of moves left, the current position of the knight, the directions array, and the memoization map. Inside the DFS function, we first handle the base cases. If the knight moves out of bounds, we immediately return a probability of 0.0, as it's no longer on the board. On the other hand, if there are no moves left and the knight is still on the board, we return 1.0, since it has successfully stayed within bounds. Now, we need to handle the recursive calculation. First, we generate a unique key for the current state using the knight's position and the number of moves remaining. This key allows us to check if the result for this specific state has already been computed and stored in the memoization map. If it has, we simply return the pre-computed value to save time. If not, we initialize a variable, prob, to accumulate the probabilities across all possible moves. For each of the knight's 8 possible movements, we recursively call the DFS function, updating the knight's position and decrementing the number of moves left. The probabilities from these recursive calls are added together. Once all moves are processed, we divide the total probability by 8.0 to account for the average across all directions, since the knight has 8 possible moves. Finally, we store this computed probability in the memoization map using the generated key and return the result. This ensures that future calls with the same state can reuse the stored value, making the solution efficient and scalable for larger inputs. In this problem, we are tasked with calculating the probability that a knight remains on an NX in chessboard after making k moves, starting from a specific position, row, column. The knight's unique movement pattern, which forms an L shape, allows it to jump to up to 8 different positions from any square on the board. To solve this, we use a recursive depth-first search, or DFS, combined with memoization. This means we systematically explore all potential paths the knight can take, and we store the results of previously computed states to avoid redundant calculations. The base cases for our recursion ensure that if the knight moves off the board, the probability is 0, and if no moves are left, the knight is guaranteed to remain where it is, giving a probability of 1 for that state. These concepts provide the foundation for our solution approach. Let's explore an example with input n equals 3, k equals 2, row equals 0, column equals 0. The chessboard is 3x3, the knight starts at the top left corner, 0, 0, and it has 2 moves remaining. From this position, the knight has 8 possible moves, but not all of them will land within the board. For instance, if the knight moves to 2, 1, we make a recursive DFS call to calculate the probability of staying on the board from that position with 1 move left. However, if the knight attempts to move to 2, -1, that position is out of bounds, and the probability for that path is 0. Similar calculations are performed for all other possible moves. As we compute these probabilities, we store intermediate results in a memoization dictionary. For example, the probability of staying on the board from 2, 1, with one move left may be calculated as 0.25, and this value is saved to avoid recalculating it if the same state is encountered again. Finally, we aggregate the probabilities from all valid moves and divide by 8, since the knight has 8 potential moves in total. After completing the recursive computations for all valid paths, the total probability of the knight staying on the board after 2 moves is determined to be 0.0625. Now, let's look at another example with input, n equals 3, k equals 1, row equals 1, column equals 1. Here, the board remains 3x3, the knight starts in the center at 1, 1, and it has only one move. From this position, the knight has 8 possible moves, all of which are initially considered. However, several moves, such as 2, 3, 2, or 3, 0, are out of bounds and contribute a probability of 0. For the moves that remain within bounds, the knight ends up with no moves left, meaning the probability for those paths is 1. This simpler scenario demonstrates how the base cases of our recursion handle the termination of valid paths and the elimination of invalid ones. During this example, memoization continues to play a critical role by preventing redundant computations for states that are visited more than once. With only one move, the knight has 8 possible moves, but only 4 of them remain on the board. By summing the probabilities of these valid moves and dividing by 8, we calculate the total probability of the knight staying on the board after one move as 0.5. Finally, in a larger example, such as n equals 8, k equals 3, row equals 4, column equals 4, the increased board size and move count lead to deeper recursion. However, the use of memoization ensures that overlapping subproblems are efficiently handled. The final probability is derived by summing the probabilities of all valid paths and dividing by 8 at each recursion level. This problem highlights the importance of memoization in reducing time complexity, transforming an exponential problem into one that is polynomial. By using recursive DFS, we explore all possible paths while maintaining clarity and efficiency, making this approach robust even for larger inputs. To analyze the time complexity of the algorithm, we need to consider 3 main aspects: the recursive depth, the number of memoization states, and the time spent per state. First, the recursive depth is dictated by the number of moves, k, since with each move, the helper function DFS is called. This gives us a recursive depth of O, k. Next, the memoization states store results for unique combinations of the knight's position, R, C, and the remaining moves. Since the chessboard has n*n positions, and for each position there are k possible remaining moves, the total number of states is O, n²*k. Finally, for each state, the algorithm evaluates up to 8 possible moves of the knight, which requires O, 1, time per state since 8 is a constant. Combining these factors, the overall time complexity is the product of the number of states and the time spent per state, resulting in a time complexity of O, n²*k. Now let's discuss the space complexity. The space usage is influenced by 2 factors, the memoization storage and the recursive call stack. The memoization dictionary, memo, stores results for up to n*n*k states, where each state requires constant space. This gives a space requirement of O, n²*k, for memoization. Additionally, the recursive call stack depth is at most k, leading to a stack space usage of O, k. When we combine these, the total space complexity becomes O, n²*k, plus O, k, which simplifies to approximately O, n²*k. Comparing this to a brute force approach without memoization, we see a significant improvement. A brute force method would involve recomputing probabilities for overlapping states, resulting in an exponential time complexity of O, 8 to the power of k, as each move generates up to 8 recursive calls. By leveraging memoization, the provided algorithm avoids redundant computations and achieves a polynomial time complexity of O, n²*k. The algorithm's best, worst, and average case complexities further highlight its efficiency. In the best case, if k equals 0, meaning no moves are made, the algorithm immediately returns a result with a time and space complexity of O, 1. In the worst case, the algorithm evaluates all possible n²*k states, leading to a time and space complexity of O, n²*k. The average case is similar to the worst case because the algorithm uniformly explores all reachable states. Mathematically, the time complexity arises from processing each state, R(C) moves underscore left, exactly once, where there are O and squared asterisk K states, and each state requires constant time for evaluating the 8 possible moves. Therefore, the total time complexity is O n squared asterisk K. Similarly, the space complexity accounts for the O n squared asterisk K memoization storage and the O K recursive stack depth, resulting in an overall space complexity of O n squared asterisk K. By implementing memoization, the algorithm achieves polynomial efficiency, a significant improvement over the exponential complexity of a brute force approach. When solving this problem, there are several common pitfalls to be aware of. First, it's easy to overlook edge cases, such as when the knight starts near the edge of the board or when the number of moves allowed is 0. Testing your solution with scenarios like the smallest board size, maximum moves, or corner positions is critical to ensure robustness. Another mistake involves underestimating the depth of recursion in brute force solutions. Since the number of recursive calls grows exponentially with the number of moves, failing to account for this can result in stack overflow or inefficiencies. Using techniques like memoization can help mitigate this. Additionally, it's important to validate moves properly. If you don't check whether a move keeps the knight on the board, you could end up accessing invalid indices, leading to unexpected errors. Inefficient state representation is another issue to avoid. Choosing overly complex data structures can waste memory. Instead, opt for simple, compact representations that still capture all necessary information. Lastly, failing to optimize repeated computations is a major inefficiency. Without dynamic programming or memoization, your solution may repeatedly recalculate results for the same state, significantly increasing runtime. This problem isn't just about solving it, it's also about how you approach it during an interview. Interviewers often use this problem to test your ability to identify patterns in movement and apply optimizations like memoization or dynamic programming. It's important to understand the trade-offs between different approaches. For instance, while brute force is straightforward, it has a time complexity of O(8 to the power of K, which is impractical for large inputs. Dynamic programming, by contrast, reduces this complexity to O(n*m*k by leveraging previously calculated results. Be prepared to explain these trade-offs clearly. Interviewers may also pose follow-up questions to test the flexibility of your solution. For example, they might ask you to calculate the probability of the knight staying on the board or count the number of unique paths it can take. Demonstrating how your solution can adapt to these variations shows depth of understanding. Even if you start with a brute force approach, it's crucial to articulate how you would iteratively optimize it. This progression can leave a strong impression, as it highlights your problem-solving skills and ability to refine your approach. Understanding related problems can help you build a stronger foundation for tackling this one. For example, LeetCode 980, Unique Paths 3, shares similarities in movement validation and path counting, making it a good practice problem. LeetCode 46, Permutations, focuses on building recursive intuition, which is essential for understanding how to explore possibilities systematically. LeetCode 93, Restore IP Addresses, is another useful problem for recursive exploration under constraints. These problems help reinforce skills that are directly applicable to the knight probability challenge. Now, let's consider some alternative approaches. A brute force method involves simulating all possible moves recursively. While this is an easy-to-implement solution, it's highly inefficient, with a time complexity of O(8 to the power of K. Dynamic programming offers a significant improvement by storing results in a 3D table, such as dp, x, y, moves, to avoid redundant calculations. This approach is much faster but uses additional memory. Another option is breadth-first search, which explores all valid moves iteratively, layer by layer. This method avoids recursion and stack overflow but may not be as fast as a well-optimized dynamic programming solution. Finally, let's discuss memoization, which is another powerful optimization technique. By caching the results of recursive calls, you can avoid recalculating the same state multiple times, which drastically improves time complexity. Memoization is particularly useful because it requires minimal changes to your existing recursive solution, making it a relatively easy optimization to implement. However, managing the cache carefully is important to ensure correctness, especially when dealing with overlapping subproblems. This approach strikes a good balance between efficiency and simplicity, making it an excellent choice for this kind of problem. Thank you for following along. In this session, we tackled the knight probability and chessboard problem and explored how dynamic programming can simplify complex state-based challenges. Remember to practice similar problems to solidify your understanding, and stay tuned for more engaging content. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!